All right, so we've done one example of solving a system of linear DEs using Laplace transforms. We're going to want to do one more just to get a little bit more experience with it, this time with second order equations. So here's our system. We can see it's second order equations in each case, and then we have some initial conditions to work with here. So I'm going to start the same way that I did before. Take Laplace transforms of both sides of our equation. Notice I don't need to move anything around this time. I have all of my derivatives of x's and y's and everything on the left side already. So taking Laplace transforms of both sides, I'm going to have the Laplace transform of, let's call that x double prime, plus the Laplace transform of x prime, plus transform of y prime equals 0. And then in this case, looks kind of similar. Transform of y double prime plus transform of y prime minus 4 times my transform of x prime. And that equals 0 as well. Notice I would have taken the Laplace transform of 0 in both of these cases, but the Laplace transform of 0 is 0. And hopefully you can verify that. It's pretty straightforward just using the definition of the Laplace transform. So let's expand all of this stuff using the same stuff we've been doing. So this is going to look like s squared x of s minus s, I don't need that, x prime, x, made kind of a mess of that. Let's do that down here. Okay, let's try that again. So it's going to look like s squared x of s minus s x of 0 minus x prime of 0. That's my first transform. Plus the next transform is going to look like s x of s minus x of 0 plus s y of s minus y of 0 equals 0. So it kind of expands out into this long thing that we'll simplify. Second equation is going to look like s squared y of s minus s y of 0 minus y prime of 0 plus s y of s minus y of 0 minus 4 times s x of s minus x of 0 equals 0. So we have a lot of simplifying to do. We can use our initial conditions to definitely simplify a lot of this. But let's see, I have an s squared and an s both being multiplied by x of s, so I can collect those and factor the x of s out, leaving me with s squared plus s, or let's do this over here. This will look like s times s plus 1 after factoring x of s. Whoops, there we go. Okay, so that takes care of these two terms. And then x of 0 is equal to 1, so this becomes minus s times 1, or just minus s. X prime of 0 is equal to 0, so I'm not going to write anything there. I've dealt with this term. Minus x of 0, that's minus 1 from our initial conditions, plus sy of s, so plus sy of s, minus y of 0, which is negative 1. So minus negative 1, that's plus 1. And that equals 0. And notice I have a negative 1 and a positive 1 that will cancel each other there. Same thing down here. We want to simplify this guy. So I'm going to have s squared y of s plus sy of s, collecting those terms and factoring the y of s out. I also have s times s plus 1 y of s. Okay, and then I'm going to have minus sy of 0. Y of 0 is equal to negative 1, so that becomes a plus s. Minus y prime of 0, which is 5, so minus 5. We've dealt with that term already. Minus y of 0, which is negative 1, so minus negative 1, that's plus 1. Minus 4 times s x of s, so minus 4s x of s, minus x of 0, which is 1, times negative 4 would be negative, or sorry, minus 4 times minus 1 would be positive 4, so plus 4 equals 0. And again, notice 1 plus 4 is 5, minus 5 is 0, so we get to cancel all of those constants as well. Now notice a couple of things in both equations. First of all, each equation, each term in the that's remaining in each equation has a factor of s appearing. So we can divide everything by s in both equations. And then secondly, we have this term here that needs to be moved over to the right in each equation to isolate the x and the y, keep those on the left. So after dividing everything by s, this will look like this. S plus 1, x of s, plus y of s, equals, I've divided this by s, so it's negative 1. I add it over and it becomes positive 1. Here we're going to have, let's have the x term show up first so things line up. Dividing that by s gives me negative 4 x of s plus s plus 1 y of s. And again, I would have divided that by an s, giving me a 1. Subtracting it over gives me a negative 1. Okay, so that actually simplified things down a whole lot. Now, at this stage, what we want to do is eliminate one of our variables. In this case, I'm going to eliminate the x first. So I need to multiply my top equation by 4 and my bottom equation by s plus 1 in order to do that. 4 s plus 1. I'll multiply through and then add. So that's going to eliminate these x's, and then I'm going to get a 4y of s. Okay, plus s plus 1 times s plus 1, so plus s plus 1 squared y of s. And then I'm going to get a 4 here, a negative s, and a negative 1, so that's going to equal negative s plus 3 after adding those terms. Okay, let's combine these. So if I were to square s plus 1, that's s squared plus 2s plus 1. Add this 4 right here, and I get s squared plus 2s plus 5 y of s equals negative s plus 3. Okay, now isolate my y of s. So this would be negative s plus 3 over s squared plus 2s plus 5. Okay, now this doesn't factor very nicely, but what would be useful is actually completing the square on this guy. We'll use one of our translation properties that we've talked about. So notice this is the same thing as negative s plus 3 over. So if I complete the square, s squared plus 2s plus 1 is a perfect square. That would leave me with plus 4 here. So I have s plus 1 squared plus 4 is what that would look like after completing the square. And thinking ahead a little bit, I know that I want to find an inverse transform of this guy, which means I would want to split this up into a numerator that involves just a constant and a numerator that involves a linear term or linear function, something involving the s. Also, because I have this s plus 1 in parentheses here, I'm anticipating using that, property of that translation property. So I'd like for an s plus 1 to be appearing in my numerator to match what I have here. I don't have an s, though. I have a negative s. So notice, one thing I could do, I could write this as negative s plus 3 minus 1 plus 1 over s plus 1 squared plus 4. I'm kind of running out of space there. So what does that do for me? Well, y of s. If I collect the 3 and the 1, the plus 3 and the plus 1, that gives me 4 over s plus 1 squared plus 4. That leaves me with negative s minus 1. And if I take the negative out, that becomes s plus 1 up in my numerator. So I have s plus 1 squared plus 4. And again, the goal there was to get a numerator of s plus 1 that would match the s plus 1 here. That allows me to use my translation property. Okay, so from the translation properties that we talked about previously, taking an inverse transform of this guy, that s plus 1 there is going to introduce a factor of e to the negative t. Okay, and then we just treat this as if it were an s. So this would, when I take my inverse transform here, what are we going to get? Well, this is of the form, sorry, this is of the form where we would be getting a sine. So the 4 is equal to 2 squared. I should be seeing, sorry, let me write this a little bit differently. 2 times 2 over s plus 1 squared plus 4. That'll make it a little bit more clear what it is we're looking at here. Minus s plus 1 over s plus 1 squared plus 4. Right, so now this is in the form that we want it to be. Remember, that should be a k where this is a k squared. So in this case, k is 2. And then I have this 2 out here. The inverse transform is going to give me 2 sine of 2t. But I need that extra factor, actually. Sorry, this is going to be y equals 2e to the negative t. That e to the negative t comes from our translation property there. Sine of 2t. And then the transform of this guy is going to be minus e to the negative t cosine of 2t. Okay, so that gives me my y. Now, in the previous example in the last video, we found that it was helpful to make a substitution where we said, here's our y. We can find y prime, substitute it in for an equation where a y prime appears, and then isolate x. The problem, however, here is that neither of our equations involves the x explicitly. We have derivatives of x. We have a second derivative of x and a first derivative of x. But there's no x just appearing by itself, so we wouldn't be able to algebraically solve for it. Instead, what we want to do is go back to the system that we came up with here and redo the elimination, but this time eliminate the y variable instead of the x. So I'm going to rewrite that system. It was s plus 1 x of s plus y of s equals 1, and negative 4 x of s plus 1 y of s equals negative 1. Okay? Now I want to eliminate my y. So in order to do that, I can multiply this equation by an s plus 1, and this equation by a negative 1, so that I have s plus 1 as a factor here and a negative s plus 1 as a factor here, which will cancel those. That's going to give me s plus 1 squared, x of s right here. Negative 1 times negative 4 is plus 4, so I'm going to get plus 4x of s. We know that the y's will cancel. And then I'm going to have s plus 1 times 1, so s plus 1, plus the 1 that I would get here. So that equals s plus 2. Okay? If I factor the x of s out, notice I could do what I did before, or I could even just write it this way. X of s times s plus 1 squared plus 4. Since we already know we want it in that form anyways, equals s plus 2. Isolate my x of s, so I'm going to get x of s equals s plus 2 over s plus 1 squared plus 4. And once again, we would like a numerator of s plus 1, so we can match it with this s plus 1 and use our translation property again. That's easy enough to do. If I just borrow a 1 from that 2 right there, I can write this thing this way. S plus 1 squared plus 4. Okay? Now notice we need this guy to be k, where this is k squared, because when I take my inverse transform, this is almost of the form of that sine function. But if that's the case, then I actually need a 2 to appear up here. So if I were to make that a 2, I would also need to be multiplying by 1/2 to help cancel that. Okay, so now taking an inverse transform of both sides, this, where I use my translation property, would give me e to the negative t cosine of 2t. Here I'd have plus 1/2, and this would just look like e to the negative t again. My translation property is being used here. sine of 2t. Okay? And so there's my solution to that system. Again, this doesn't seem like it's any quicker than what we were doing with elimination. It's just showing how Laplace transforms also work as a tool in solving systems of equations. But like I said, we're going to be dealing with systems of equations in more generality in Chapter 8. That's going to wrap things up for Chapter 7.